All right, we're going to add one more tool to help us figure out the which roots to use or how to find all the roots of a polynomial function. And this rule is called Descartes' rule of signs. So we're just going to start off by giving you the rule and then working a couple of examples and kind of doing one where we pull everything together where I can show you how to start from scratch to find all the roots of a polynomial function. So here's Descartes' rule of signs. So here's the first part. If p of x is a polynomial function and p of x has real coefficients, which is pretty much all the ones we deal with, then this is true. The number of positive real zeros of p of x is equal to the number of sign changes in p of x, or less than that by an even whole number. So you're going to count the sign changes. You're going to count how many times in the polynomial that we switch from a positive term to a negative term, or a negative term to a positive term. And in p of x, the number of those sign changes, that's how many positive real zeros you're going to have, or it's going to be less than that by an even whole number. So if you count 3 sign changes, then you're going to have 3 or 1 positive roots, real zeros. If you count 2 sign changes, then you're going to have 2 or 0 positive real zeros. So that's the first part. The second part deals with the number of negative real zeros. So for the negative real zeros, the number of negative real zeros of p of x is going to be equal to the number of sign changes in p of negative x. So we're going to replace x with a negative x. That's going to change some terms, it's not going to change other terms, or less than that by an even whole number. So it's the same process. For the positive ones, we're looking at p of x. For the negative ones, we are looking at p of negative x. So we're going to work an example to demonstrate what this is all about. All right, we have a polynomial function here, 2x to the 4th minus x cubed minus 2x squared plus 5x plus 1. And all we're going to do is use Descartes' rule of signs to determine the possible number of positive and negative zeros for this polynomial. So looking at the positive one, I'm going to start. I start with a positive term, and then I'm immediately turning it into a negative term. So there's one sign change. And then he's negative, and he stays negative, but here he turns back to positive, and then he stays positive. So we have 2 sign changes in this polynomial. So 2 sign changes. That means we have 2 or 0 positive real roots. 2 or 0. We're not going to have 3, we're not going to have 1. It's either going to be 2 or 0. So now we do the same thing for the negative roots, but first I have to evaluate p of negative x. So think of your end behavior and what happens when I raise a negative value to an even exponent and to an odd exponent, because what I'm basically doing is replacing x with negative x. So I put the entire negative x in the parentheses and I raise it to an exponent. So this is an intermediate step. When you get good at it, you don't have to show it, but I'm showing it for your notes, so hopefully you might understand. Okay, so when I process that, it becomes p of negative x. Any even exponent does not change the sign, because negative x to the 4th is the same as positive x to the 4th. But if you look at this guy, if I raise a negative x to the 3rd power, it's going to be negative x cubed multiplied by the other negative sign, or subtraction. It's going to turn it positive. So that one does change sign. The next one does not change sign because it's an even exponent, but the positive 5x is now a minus 5x, negative 5x, or plus negative, whatever you want to say, and then plus 1. So let's count the sign changes here. I'm positive, but there I'm negative. There's one sign change. I stay negative, up, but then I go positive again. So we have 2 or 0 negative real roots. Now the fundamental theorem of algebra tells us that we're going to have 4 roots total. So chances are we're going to have 2 positive and 2 negative. And that's how you use Descartes' law of signs. Now we're going to do an example where we put everything together to try to find the roots. Alright, here's our example. I want to find all the roots of this function, x to the fourth minus 7x cubed plus 13x squared plus 3x minus 18. So we need to come up with a list of possible roots, and we want to figure out possibly how many positive and how many negative we're going to deal with. So Descartes' rule of signs we do first. We count the number of sign changes. Here's 1, 2, 3. That means we're going to have 3 or 1 positive real roots. And if you look at my total here, when I do the negative, I should probably have no more than 1 because they have to add up to 4. If I have possibly 3 positive, then I'm probably only going to have 1 negative. Let's look at p of negative x. If I replace x with negative x to the fourth doesn't change, x cubed does change, x squared does not change, x changes, and my constant term will never change. That's why it's called a constant. Now let's count the sign changes. Positive, 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 negative. 1 sign change. So 1 negative real root. Alright, I know I have 1 that's negative. So I might start, after I list all my roots, or my possible roots, I might start with the negatives, because once I find that guy, I know I don't have any more, and then I can go find the positive root. If this is a 4th degree, that means we're going to have to use synthetic division to find 2 of the roots before I can factor it or use the quadratic formula in the end. So this is going to be a little bit lengthier process. Let's now use the rational root theorem and list all the possible roots. We need to use p of x though, don't use p of negative x. So here's my polynomial. I have an 18 and I have a 1. So the factors of 18 are going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. Since the front coefficient is only 1, these are the only possible roots. We don't have any fractional roots, just these. So we're going to start the synthetic division process next. Alright, we've got our polynomial, we have our list of potential roots. We know from Descartes' rule of signs that we're going to have a negative root. So let's start by testing negative 1 and see where it goes. Let's list our coefficients, 1, negative 7, 13, 3, and negative 18. And then I'm going to start with negative 1 and see what happens. So the synthetic division process, I bring 1 down, I multiply it by negative 1, that's negative 1, so it's negative 8, so it's 8. Add those together, you get 21. Then you get negative 21, which is negative 18. Gives me a positive 18, 0. Yay, we found a root. That's the only negative root. There's no more negative ones, because that's what Descartes' rule of signs says. So negative 1 is the only negative root. So now we have to do this process again to find the positive roots. I'm not going to start with this original polynomial anymore because negative 1 works, which means if I factor out the binomial x plus 1, I'm left with this depressed polynomial, x cubed minus 8x squared plus 21x minus 18. I'm going to start here and then start dividing more things away. So I can put another box here. And now let's start with positive 1. 1, 1, negative 7, negative 7, 14, 14. No, that one's not going to work. So let's try another one. Let's try positive 2. 1, negative 8, 21, negative 18. Put him in there. Positive 2, because he's on my list up there. 1, 2, negative 6, negative 12, 9, 18. Yes, it works. So yay, we found them. So my roots are from synthetic division, negative 1 and positive 2. And now I can factor this depressed polynomial. So if I write out my polynomial, we can factor the bottom one. So p of x right now has been broken up into x plus 1, x minus 2, and now this polynomial is x squared minus 6x plus 9. Well, that's going to be x minus 3 and x minus 3. So when it's all factored out, I have x plus 1, x minus 2, x minus 3, x minus 3. So the roots in this case are -1, 2, and then a double root at 3. And that's how you find them, using all the tools that you have, the rational root theorem and Descartes' rule of signs, and then synthetic division.